Hello, I'm Luis Serrano, and this is Serrano Academy. And in this video, I'm going to tell you about the attention mechanism. In particular, we're going to go deep into key, query, and value matrices. We're going to see how the attention mechanism works like gravity, where words pull each other the way planets pull each other. And we're also going to see why these matrices are so useful in giving context to a conversation. Are you ready? Let's begin. The attention mechanism was introduced in this paper called Attention is All You Need. And as you know, the attention mechanism is what really made models like ChatGPT or DeepSeek talk so well. But how does attention work? Well, imagine that you have two people talking and one of them says the word apple. Now, the other one doesn't know what the first one's talking about because it could be the apple, the fruit, or it could be the technology brand. So what the second person would expect is more context, so they could just listen to the other person talk more. And if the other person has been talking for a long time about, say, a bunch of other fruits, then we're pretty sure that they're talking about an apple as the fruit. But if they've been talking for a while about computer terms, then probably they mean Apple, the computer brand. Now, this can be more subtle, right? You could say something like, the other day I was walking and I thought about pears, then I realized I wanted some fruit, so I thought about getting an orange, etc., etc. So some words here are important. For example, the word pears, the word fruits, and the word orange are important. And so we pay a lot more attention to those. But words like day are not so important because they don't really add context to this conversation. So the idea is that we are going to pay more attention to words that are similar to the one we are looking at right now. And so we get to a very important concept, which is the concept of similarity. The attention mechanism pays more attention to words that are similar. We need to define what a similar word is. And I like to see it as pulling. So words that are similar actually pull each other. So let's talk more about this notion of similarity. What I want is a notion that tells me when two words are similar and when they're not. For example, the words pear and apple, orange and apple, or truck and car are similar, and the words truck and apple and house and apple are not similar. And one of the best ways to define similarity is using something called an embedding. So an embedding is super important in machine learning, and I like to see it as locating words somewhere in the plane. So let's say that the word apple is here at coordinates 6, 4. What does 6, 4 mean? Well, 6 units in the horizontal direction and 4 units in the vertical direction. So let's say, for example, car is at -4, 2, because you go 4 in the wrong direction and then 2 up. And for example, condominium is here at 7 -3 because you walk 7 on the horizontal direction and then -3 because you go down by 3. So the least we can ask of an embedding is that it locates similar words in similar positions. So if we're going to have, for example, orange and pear, the fruits are going to be close to apple, and the vehicles are going to be close to car, and the houses and apartments are going to be close to condominium. That makes sense, right? That's the least we can ask of an embedding. But we can actually ask a lot more. So for example, here we're looking at embeddings of just 2 entries in the plane, but if they have 3 entries, they would be flying in space, in 3-dimensional space. And in reality, I've seen embeddings all the way to 4096. You can have hundreds of thousands of entries in an embedding, and it's just basically associating thousands of numbers to each word. Each row here is called a vector, so we associate a vector to each word. And of course, the least we can ask is that similar words have similar vectors made of similar numbers, and different words have different vectors. So if I take the vector for apple and for orange, I'm going to find a list of thousands of similar numbers. But I like to see embeddings as more. I actually like to see them as each entry means something. So naively, we can think of maybe one entry being the color, the other one the size, and maybe other properties. But in reality, these are built by a neural network. So there's a lot of descriptions that we can't really understand as humans, but they are descriptions of the word. So if you think of an embedding as, let's say, 1,000 numbers that describe a word, each number describes in a particular feature, then that's a good way to think of embeddings. Now, embeddings really help us define similarity because we can see it as distance, right? We can think of orange and pear and Android. Let's say, for example, orange and pear are very close by, so they're very similar because their distance is very small. Whereas orange and Android are very far from each other, so they're not similar. So we're going to see later that there's better ways to define it than distance, but distance is a good way to define it. However, embeddings are not perfect. Let's say that I have a bunch of fruits over here, cherry, orange, and pear, and there I have all the technology things like phone, laptop, Android, and Microsoft. And the question is, where would I put the word apple? Well, that's hard, because apple could be a fruit, but it could also be a technology word. And what do? Well, we really need context, and that's where the attention mechanism comes in. So let's say that some person has been talking about them and said, I went to the store and got an orange, a pear, a cherry, and an apple. So then the words orange and pear and cherry are going to pull the word apple like a magnet pulls, or like a planet pulls another planet with gravitation. And now for the model, for the embedding, the new coordinates have changed because now apple moved in this direction, and now the embedding knows that it's a fruit. The same thing happens if instead I've been saying I need a laptop and a phone, and I'm wondering if I should get an Android, Microsoft, or Apple. Well, in that case, the words phone, laptop, Android, and Microsoft are going to pull the word Apple like gravitationally, and it's going to move down closer to the technology part of the embedding. And so now the model knows we're talking about a technology word. Now here's a small problem. Let's say that I said yesterday I bought an orange and an apple. So we know as humans that orange is the important word there. Orange is the word that is pulling the word apple. We know it's not going to be yesterday or I or bought. However, the computer doesn't really know. For the computer, every word is important. So how do we solve this? Well, let's say the word apple is here, and it's going to get pulled by all the other words in the sentence. However, if the embedding is good, orange and apple are going to be much closer than orange and yesterday, or orange and I, or orange and. And in this model, words that are close by attract each other way more than words that are far away. Just like magnets. Two magnets attract each other if they're close, but if they're far away, they don't attract each other so much. Or planets. Planets attract each other when they're close, but not when they're far away. So here, all the words pull apple, but orange pulls it a lot more. And apple also pulls orange. So after a gravitational step, they're going to be a lot closer, and the other words move too, but not so much. So it's kind of like gravitational pull with planets, right? The Earth and the Moon are very close to each other, so they pull each other, they exert a gravitational force. But for example, the Earth and Jupiter or Saturn, they don't pull each other so much. So they move a little bit, but not so much. It's really the Moon and the Earth that attract each other. So this is pretty much how attention works. But as I mentioned before, distance is not the best way to tell similarity between two words. There's two better ways at least. One of them is the dot product. So let me show you dot product. Let's say we have an embedding over here. And as I said, the coordinates in the embedding mean something. So let's say, in a nice example, that the horizontal axis means fruitness, how much something is a fruit. And the vertical axis means technology, so how technological a word is. So orange and pear are way to the right because they have a lot of fruitness. So they have the coordinates, let's say 6, 1 and 7, 2. Whereas Android is a technology word, so it's going to be way up at the coordinates 1, 8. So let's put them here. Orange is 6, 1, pear is 7, 2. And the first coordinate is fruitness, and the second coordinate is technology. And now orange and Android also have the fruitness and the technology coordinates. So we need a high similarity for orange and pear and a low similarity for orange and Android. How do we do it? Well, let's come up with the following formula. What we really want is to match the numbers that are high for the high similarity one. So for example, if we take this 6 and 7, they're both high numbers. So we really want to use that. So let's multiply them. 6 times 7. And then the next is 1 times 2. And then we add them. So we multiply the fruitness and we multiply the technology and we add them. And it's high because they both have high fruitness. Now, look at what happens here. If we take the fruitness, that's 6 and 1, that's 6. And then the technology is 1 and 8. So we're adding a 1 and an 8. And when we add that, we don't get a high number because the high numbers in these two coordinates don't match. See, the 6 is over here and the 8 is here because the words are not similar. So when we add them on the left, we get a 44. That's a large dot product. So that's going to be a large similarity. On the other hand, for orange and Android, we get 14. That's a small dot product and a small similarity. So we're really using the fact that when two words are similar, their embedding vectors have high numbers in the same position and even maybe negative high numbers in the same position. So when you multiply them, they get a high number. On the other hand, when two words are very different, their embedding vectors are going to have high numbers in different places. And when you multiply them and add all those products, you're not going to get a very high number. That's dot product. There's another way to calculate similarity, which is cosine distance. And here we're going to say, instead of looking at the distance between two things, we're going to look at the angle they form with the origin. So we're going to calculate this angle between Android and pear and between pear and orange. So When we look at the angle between Android and pair, it's a large angle because the points are far away. They create a big angle with the origin. So large angles, when you take the cosine, you get small numbers because cosine of small numbers are big and cosine of big numbers are small when these numbers are angles. And so we get a small similarity between Android and pair. On the other hand, if we take the angle between pair and orange, then that's a very small angle. So it gives us a very large cosine, and that gives us a large cosine similarity. So these two ways are very similar. As a matter of fact, they are multiples of each other because to get one, you have to scale it. The one that's used by ChatGPT and other large language models is actually a different one. It's called scale dot product, but it's basically the dot product multiplied by a different number. So for practical purposes, we can think of dot product, we can think of cosine distance, and sometimes I'll use one, sometimes I'll use the other one, and sometimes I'll be sloppy and actually use distance, but it doesn't really matter. Now the question is, are we done? We've defined similarity and we've said that words pay more attention to similar words. So maybe that's it. No, unfortunately, no, we are far from done because embeddings have a lot of problems. In particular, embeddings may not be the best at defining similarity, believe it or not. Two things being close in the embedding doesn't necessarily mean they're similar for several reasons. And that's why we define something called the keys and queries matrices. There's also a values matrices, that one comes later, but let me tell you what they are. So the question is, what is a matrix? Well, we can think of a matrix as a big array of numbers, a big rectangular array full of numbers, but that's not the way I like to see matrices. See, I think that looking at a matrix as an array of a lot of numbers is kind of like looking at a book as an array of a lot of letters. I mean, a book is an array of a lot of letters, but that's not what makes it a book. What makes it a book is that it tells a story, that it tells a beautiful story. And matrices also tell a beautiful story. So I want to go past the numbers and I actually want to look at what is the story that matrices tell us. And one of the stories that matrices tell us are linear transformations. So what are linear transformations? I like to look at them with an image. For example, this dog. What can you do to this image? Well, you can rotate it. You can also stretch it in the horizontal or in the vertical direction or pretty much in any direction. And you can also do something called the shear, which is that you turn the square into a parallelogram like this. It's kind of like putting a book on a table and pasting the bottom and then pushing the top so you get a parallelogram. And in general, a linear transformation is any combination of these. So if you rotate, you stretch, you shear, it's almost like if you take the yellow vector there and turn it into any vector, and then the blue vector and turn it into any vector, and then the square becomes a parallelogram. You could also accidentally turn it into a line and then you get a degenerate linear transformation. Those exist too, but the majority of them are not. So think about this. If you take the square and turn it into any parallelogram you want, and then the rest of the plane follows, then you have a linear transformation. Some transformations are not linear. If I take the square and turn it into a circle, that's not a linear transformation. It has to turn into a parallelogram. And that's in 2 dimensions because it's in the plane. But if I have 3 dimensions or 1,000 dimensions, it's the same thing. If you combine rotations, stretching, shearings in different dimensions, then you get something linear. And those correspond to matrices. So any matrix is a linear transformation. Any linear transformation is a matrix. This linear transformation is a 2 by 2 matrix because we're in the plane. If it's in space, it's 3 by 3. If it's in a 1,000-dimensional space, then it's a 1,000 by 1,000 matrix. But if you ask me, every time I see a matrix, the first question I ask is, what is the linear transformation that matrix defines? And in particular, if I have an embedding, I can apply a linear transformation. So let's say here I have a nice embedding where the horizontal axis gives me the size of something and the vertical axis gives me the animalness. So animals are on top and non-animals on the bottom. And then as you move to the right, you get bigger and bigger. So we have a little rabbit that's small, but it's an animal, an elephant that's big and animal, and then a truck that's not an animal, but it's big. And I could apply a linear combination to this and get something like this, where the axis now means something else, and the animals and the truck moved around. And who knows, maybe this embedding is better than that one over there. Why would it be better? Let me get to that. So actually, you're going to tell me why embeddings are better when they get transformed. Let's do a quiz. We have embedding 1 over there, we have embedding 2 over here, and then we have embedding 3 over here. Now, help me out. Which one do you think is the best of these three? And which one do you think is the worst of these three? This is a conceptual quiz. You may differ from my answer and maybe we're both right. But I encourage you to pause the video and maybe think of which one you like more. So let me tell you what I think. I think the middle one is the best. And the worst one is this one over here at the right. And the one on the left is kind of so-so. Why? Well, in my head, an elephant and a rabbit are more similar than an elephant and a truck because they're both animals, right? They could be in the same conversation. On the other hand, elephant and truck, they do have the same size and maybe similar weight, but they're not that similar. And in embedding 2, elephant and rabbit are very similar, more similar than elephant and truck. On the other hand, in embedding 3, an elephant and a rabbit are very different and way more different than an elephant and a truck. And in embedding 1, it's almost the same similarity between elephant and rabbit and between elephant and truck. So in my mind, embedding 2 is the best because it makes the animals more similar to each other and doesn't pay so much attention to size. On the other hand, you could say that this third one is the best. Say if you're loading a ship and you care about weight more than anything else. So there could be different opinions, and we'll see later in multi-head attention that you can actually fit all these opinions and get the best of them. But for now, let's imagine that the best one is embedding 2. And what I'm saying here is that some features may be more important to tell similarity and some features may be less important. So let's say, for example, that we're comparing two people. We're trying to see how similar they are. And we have several features that describe these people. So for example, we have age. If two people have the same age, maybe they're likely to be similar, maybe not. If they have the same place of birth, then maybe they're more similar. But something like what day of the week were they born? If you were born on the same day of the week as someone else, that doesn't mean you're similar. You could be completely different because that's kind of a random feature. So we would want to diminish that. So for example, let's say we multiply age by 1. Let's say we multiply place of birth by 1.1 because it's more telling if you're similar. But day of the week you were born, you want to really diminish it. So let's say you multiply it by 0.1 to really remove its importance. So this transformation from an embedding to a different embedding that is more descriptive of similarity is given by a matrix. So how is this matrix built? Well, the first row, age, is multiplied by 1 and you don't add any of the other features. So the first row is 1, 0, 0. For the second row, then the place of birth is multiplied by 1.1. So you put it in the middle. And for the third one, you put a 0.1 here because that's how much you multiply the day of the week that the person was born. Why are there a bunch of zeros? Because we're not adding features to each other. That's something we're going to do later. But this is the linear transformation that's going to turn this embedding into a better one that is able to tell similarity. So let's go back to the elephant, rabbit, truck example, and we're going to do something like that. So we're going to take this feature called size, and we're going to make it smaller. I'm going to keep animalness the same. So we're going to have a new embedding over here. And let's say the size, we're going to multiply it by a small number, say 0.3. So the 1 becomes a 0.3, the 0.1 becomes a 0.03, and the 1 becomes a 0.3. But we're going to keep the animalness the same. So it's going to be 1 for the elephant, 1 for the rabbit, and 0 for the truck. And so the matrix is going to be 0.30 for the top row, and 0.1 for the second row. If the matrices are making sense, then that's fantastic. But if they're not, don't worry about it. Just look at the linear transformations that we're making, and that's just as good. And so what do we get for linear transformation? We get this, where the size got reduced to 30% of the size, yet the animalness stayed the same. So we just stretched it. In this case, we compressed it. And in this new embedding, well, the rabbit and the elephant are more similar than the elephant and the truck. If you want to keep track of coordinates, these two rows correspond to size and animalness, and the columns correspond to the new size and the new animalness. So as you see, we can stretch and compress these dimensions in order to get a better embedding that would be more effective at telling us if two things are similar or not similar. However, that's not the end of the story, because you don't only want to stretch dimensions, you also want to combine dimensions, add one dimension to another one, and so on. Let me show you with an example. So let's look at this example. In this example, we have two students. They're very good students. Their names are Aisha and Beto. And Aisha really loves math. Math is her favorite subject. And we have an embedding where the first column or the first dimension tells you if math is your favorite subject. So you have a 1 if math is your favorite subject and a 0 if math is not your favorite subject. Beto is also a very good student and physics is his favorite subject. So physics is the vertical dimension. That means if your favorite subject is physics, then you have a 1. And if it's anything else, then you have a 0. Looks like a pretty unforgiving embedding, but that's okay. We'll fix it. So the embedding looks like this. And now I'm going to ask you for your opinion. Which of the embeddings is better for this case? I have embedding 1, embedding 2, and embedding 3. So which one do you think? Feel free to pause the video and tell me which of the 3 embeddings looks better to you. And now I'm going to tell you my opinion. My opinion is that the best one is this embedding over here. And the worst one would be this one here. And the first one is so-so. Why? Well, in my head, if your favorite subject is math, then you probably like physics. And if your favorite subject is physics, then you probably like math. So Aisha and Beto are more similar than we think. See, the first embedding makes them really far away, and the last embedding makes them really, really, really far away. But I want them to be close, so I want this embedding over here because they're similar people. Of course, again, you may think, well, maybe physics and math are very different. Maybe I want this embedding instead. Yeah, that's completely fine, and we'll see in multi-head attention how we can combine these things. However, for now, let's say that the middle embedding is the best one. So how do we get the matrix for the middle embedding? Well, again, these two students are too far, and we want to make them much close. So we're going to create a new embedding here, and I'm going to say, okay, I'm going to look at math. If math is your favorite, then that information is going to pass to the new embedding. That's going to be a 1 over here. But if you like math, then let's add, for example, 50% to your physics score. Because let's say if I love math, then maybe I love physics 50% at the very least. So we put that as a 0.5 in this matrix, and now Aisha's vector is not 1, 0, but it's 1, 0.5. So we move her up half a unit. That means she loves math and she likes physics. Now let's do the same thing with the physics student. So if physics is your favorite subject, that's going to add 50% to the entry of how much you like math. And that's a 0.5 here in the matrix. And then we're going to keep the physics is your favorite subject score as 1. So Beto's new vector is not going to be 0, 1. It's going to be 0.51. That means if he loves physics 1 unit, then he loves math 0.5 units. That makes sense, right? So we're going to move him 0.5 units towards the right. And in the matrix, we're going to have a 1 over here. So now Aisha and Beto are much closer. We moved them much closer because they're similar people. And that's a linear transformation. The linear transformation given by this matrix is very interesting because check this out. This column over here means that to the math score, we're going to add 50% of the physics score. And that becomes this new edge over here. That's our new axis. It went from this horizontal to this diagonal. And the same thing with the other axis. We're going to take the physics axis, which is the vertical, and add 50% of the math one. And now our new axis is this one over here. And so that square over there becomes this parallelogram. And the kids are now in these positions, so they're very similar. So in other words, we took the linear transformation that turned that square into this parallelogram, a parallelogram that keeps the students in a position that is better for our embedding because it tells us they're more similar, whereas the embedding over there tells us they're not very similar. So what do we have so far? We can stretch and compress dimensions, and we can unite them and add them. So is that the end of the story? That's still not the end of the story because now we get to the really weird part. And the really weird part says that the pull between two words does not have to be symmetric. What do I mean by this? Well, let's see. So before we had word 1 and word 2, and there was a similarity between them. And that similarity told us how much they pull each other. If they're very similar, then they pull each other a lot. And if they're very different, then don't pull each other a lot. In other words, if they're close, there's a strong attraction. And if they're far away, there's not a strong attraction. However, you'll be surprised to see that in language, sometimes this doesn't happen. Sometimes word 1 will pull word 2 a lot more than word 2 pulls word 1. And that actually happens in gravity, right? Like if I have a huge planet like Jupiter, and a very small one like a moon, then Jupiter pulls the moon a lot more than the moon pulls Jupiter because the gravitation of Jupiter is much bigger than the gravitation of the moon. Well, the same thing happens in word embedding, but you'll be surprised to see that it's the opposite. It's the small word, the one that pulls the big word more. And that makes sense if you think about it, right? Because a word that's big is a word that's very popular. that word gets pulled into a lot of conversations because it will appear in many places. On the other hand, a small word that is not very popular is not likely to be pulled. That word pulls other words. So the more popular the word, the more it gets pulled, and the more strange the word is, the more it pulls other words. So here's my favorite example. My favorite example is the word fisherman and the word net. So net is a much more common word than fisherman. So fisherman pulls the word net a lot more than net pulls the word fisherman. Why? Because if I'm talking about a fisherman, it's very likely that the word net will come up. On the other hand, if I'm talking about the word net, maybe I'm talking about a badminton or a tennis net or the internet or anything like that. So it's not entirely likely that the word fisherman is going to show up in the conversation. Maybe it will, but it's likely that it won't. Think about it this way. If there's a movie called The Fisherman, it's very likely that a net will appear in this movie. On the other hand, if there's a movie called The Net, it's not very likely that a fisherman is going to show up and teach us how to catch a red snapper or something like that. So what I'm saying is that the word fisherman will pull the word net into the conversation in a much stronger way than the word net will pull the word fisherman. And the word net is bigger, so it's more popular. The fisherman is the small word. So let's look at the two cases. How much fisherman pulls net and how much net pulls fisherman. I'm going to introduce some terminology. The word that pulls is going to be called the key, and the word that is pulled is going to be called the query. Now let's come up with an embedding. I only use very nice and hypothetical embeddings in my example. So for this embedding, the horizontal axis is going to be the amount of fishing that's on the word, and the vertical axis is going to be the amount of technology that is in the word. So that's our embedding. So fisherman is over here because there's a lot of fishing and not so much technology, and then net could be somewhere here. It could really be anywhere in that diagonal. I'm going to move it around later. But let's put it somewhere in the middle with some fishing and some technology on it. And I could do any linear transformation here. For example, I could turn it into this one over here where I have a fisherman and the net. However, no matter what I do to this embedding, the similarity is going to be the same number, and the pull from fisherman to net and from net to fisherman is going to be the same amount. I don't want that. I want an asymmetric pull. I want the pull to be stronger from fisherman to net than from net to fisherman. So what can I do? Well, I think the problem is that we're looking at only one transformation and we need to look at two transformations. So we're going to have one transformation for the keys, the ones that pull, and one transformation from the queries, the ones that get pulled. And these two completely different transformations are going to give us what we want. So let me give you a small, slightly magical looking example. In the top, we're going to use these two embeddings to calculate the pull that fisherman does on net. And on the bottom, we're going to use these two embeddings to calculate the pull that net does on fisherman. And before I modify these embeddings, I'm going to show you what's going to happen. We're going to take the angle from the keys. So the keys is the fisherman and the queries is the net. So we're going to take the key in the first embedding and the query on the second embedding and calculate their angle because we're going to do cosine distance. And in the bottom, we're going to take the key as the net and the query as the fisherman and calculate the angle. So it's different. Now, in this case, we get the same angle, so it's not going to help very much. But look at what happens the moment I modify these embeddings. So I'm going to modify the first embedding using a linear transformation of the matrix 0, 0.3, 0, 0, and 1. That's going to stretch the horizontal axis and actually compress it. So we get this modified embedding over here. And for the queries, I'm going to take the matrix 1, 0, 0, 0.3, which is going to compress the vertical dimension, and we're going to get this over here. And now I'm going to take the angle between the keys and the queries. So for the first example, how much fisherman pulls net, I'm going to take fisherman as the key, net as the query. So I'm going to take the angle between fisherman on the first embedding and net on the second embedding. And that angle is this much, it's almost 0. And for the second example, how much net pulls fisherman, I'm going to take the angle between net, which is the key on the first embedding, and fisherman, which is the query on the second embedding. And how much is this angle? A much bigger angle. That's exactly what we wanted, because a small angle gives us a large cosine distance and a big angle gives us a small cosine distance. So on the top, we get a strong pull, and in the bottom, we get a weak pull. And so we got exactly what we wanted. So the moral is, if you modify the key matrix in the same way and the query matrix in the same way, but in a different one as the key modification, then you can play with these angles and get a strong pull from fisherman to net and a weak pull from net to fisherman. Now, as I said, this example looks a little magical. I moved around the embeddings for them to work, but let's look at an example that's a bit more numerical, and I'm going to change the setting. So this over here is me. And let's say that I'm a huge fan of Taylor Swift. Humongous fan. I have all the posters in my room. I go to all the concerts. I talk about Taylor Swift all the time. So the pull from me to Taylor Swift is big. However, she doesn't know me, so the pull from her to me is very, very weak. And what do I mean by this? Well, if she's over here in the embedding and I'm way over there and there's a conversation about me, it's likely that Taylor Swift will show up in this conversation because, as I said, I talk about her all the time. So people will say, well, hey, where's Luis? Oh, he's at the Taylor Swift concert. So she should be closer to the embedding because I pull her. But in the other hand, if the conversation is about Taylor Swift, if two random people are talking about Taylor Swift, it's very likely that they're not going to be talking about me. So I should not move around. I should stay where I am in the embedding. So we have an asymmetric pull because the pull from me to Taylor Swift is strong because a conversation that includes me will likely include her later. But the pull in the other direction is not so strong because if there's a conversation about Taylor Swift, it's very likely that I'm not going to show up in that conversation. So in this case, Taylor Swift is the big popular word and I am the less popular word, but I'm the one who will exert a gravitational pull, and the gravitational pull in the other direction is not going to be that big. So let's put some numbers to make this more clear. I'm going to come up with an embedding that is a little strange, but bear with me, okay? For the example, this works. So let's say that the embedding has one entry that defines if you're a Swiftie or not, and another one if you're a Lewis fan or not. So my scores are 1 for Swiftie because I'm a huge Taylor Swift fan, and obviously 1 for Lewis fan because I'm a fan of myself. And there's more entries in the embedding. There's 1 for is Taylor Swift, and there's 1 for is Lewis. So I get 0 on the is Taylor Swift because I'm not Taylor Swift, and I get 1 for the is Lewis because I am myself. It's a weird embedding because I'm the only person who gets a 1 there and she's the only person who gets a 1 in is Taylor Swift. So it's a weird embedding, but let's continue with it just to see how things work. So now, what is the embedding vector for Taylor Swift? Well, she's definitely a Swiftie. I'm assuming she's a fan of herself, and she's not a fan of me, so that would be a 0. But for the sake of having some numbers here, let's say 0.01. So she's a fan of me 1% with a 1% margin of error. And then on the is Taylor Swift, she gets a 1 because obviously she is Taylor Swift. And on the is Lewis, she gets a 0 because she's not me. So these are the embedding vectors. Now, if we're going to calculate the similarity between Taylor Swift and myself, dot product's not going to work so well because take a look at it. Dot product takes the product of each corresponding entry in the columns and adds those products together. There's a huge number here, which is we're both Swifties, so we get a 1 times 1. And so when you add these products, you get a large number, but I don't need a large number. I need a large number for how much I pull her, but a small number for how much she pulls me. So we're going to play around with this dot product and I'm going to show you how. Let's say that we're going to look at how much I pull Taylor Swift, which is a big number. What I really want to match is not the columns here. I want to match some columns with some other columns. What tells that there's a strong pull from me to Taylor Swift? Well, this number over here that says that I'm a Swiftie, and this number over here that said that she is Taylor Swift, because the moment those two numbers activate, you have Swiftie and is Taylor Swift, there's a strong pull. So we want to multiply these two numbers. The key is how much I'm a Swiftie, and the query is how much she is Taylor Swift. So when you multiply these two numbers, you get 1, which is a strong pull. Now, if we want to see how much she pulls me, that is a weak pull, then we need to look at the entry of how much she is a Lewis fan, which is a very small number, and match that with how much I'm Lewis, because that would be a pull. And so when we multiply these two numbers, we get a small number, which is 0.01. So now we got our asymmetry. So the idea is that we want to match some entries on the top with some different entries on the bottom and vice versa. Now let me come up with a slightly more realistic embedding. In this slightly more realistic embedding, you have the following entries. Does somebody like pop music? Does somebody like machine learning videos? Does somebody make pop music and do they make machine learning videos? So I like pop music, I like machine learning videos, I don't make pop music and I do make machine learning videos, so that's my vector. And Taylor Swift vector says she likes pop music, maybe or maybe not. I don't know if she likes machine learning videos, but let's say she doesn't have time to watch machine learning videos, so I put a 0.01 on likes machine learning videos. She makes pop music, so that's a 1, and she makes ML videos. She doesn't, as far as I know, so that's a 0. And to calculate how much I pull Taylor Swift, then you match these two. How much I like pop music, that's the key, that's the puller, and how much she makes pop music, which is the pulled, which is the query. So when we multiply these two numbers, we get 1, which is a strong pull. On the other hand, if we want to see how much she pulls me, we have to see how much she likes machine learning videos and how much I make machine learning videos, and those numbers we multiply. So that pull is the product of those two numbers, which is 0.01. Now the question is, how do I take a dot product by not matching corresponding things in a column, but actually by combining different columns? That is when the key and query matrices show up. We have some features which are key features. These are the features that would pull another word, for example, like pop music and like ML videos. And then we have some query features that are the ones that get pulled. If you make pop music or you make ML videos, then you get pulled into other conversations. And if you want to find out how much I pull Taylor Swift, then we have to match my keys with her queries and multiply each corresponding number and then add them. So we get 1 times 1 plus 1 times 0, which is 1. That's the amount that I pull Taylor Swift. On the other hand, if we want the opposite, how much Taylor Swift pulls me, we have to match her keys with my queries and then multiply each pair of numbers 1 times 0 and add them to 1 times 0.01, and we get 0.01, which is the amount that Taylor Swift pulls me. So now the question is, how do we manipulate this mathematically so that we match some features here with some different features here and vice versa? Well, for that we use matrices. And let's look at the key and query matrices and how they can help us do this magic. Let's recall, these are the key features, the ones that pull, and these are the query features, the ones that get pulled. So to extract them, we're going to use the following key matrices, this key matrix over here and this query matrix. I made them really nice to work out with this example, but in reality, they'll be big, messy matrices. So when we take my embedding vector times the key matrix, what happens here? Well, this part over here is an identity matrix, and that gets multiplied by that first part of the vector, the key matrix, and it basically makes a copy of it. And this part over here is a zero matrix, so it kills the second part of the vector. So we only get the keys for my embedding vector. Now, as I said, if you're not a fan of linear algebra and you don't care about matrix multiplication, don't worry. Just think about a way to extract the keys and extract the queries. But if you like matrix multiplication, then you're going to love this because the query matrix also does its job. This part over here is the zero matrix, so it basically kills the first part of my embedding vector, the keys. And this part over here is an identity matrix, so it pretty much makes a copy of the queries part of my embedding. So we get exactly what we wanted. Now, if we have my embedding vector, Taylor Swift's embedding vector, and we see how much I pull her, we extract my keys and take the dot product with her queries. That means we take my embedding vector multiplied by the key matrix, we take her embedding vector multiplied by the queries matrix. My embedding vector times the key matrix is my keys. Her embedding vector times the query matrix is her queries. And then we take the dot product of the resulting my keys and her queries. And that's going to be 1 times 1 for I like pop music, she makes pop music, and 1 times 0 of I like ML videos and she makes ML videos. So we get a dot product of 1. And if we want to see how much I pull Taylor Swift, then we take her embedding vector multiplied by the keys matrix, my embedding vector multiplied by the query matrix, and that's the way we extract her keys and my queries. So we get my queries, her keys, and the dot product of these are, well, how much she likes pop music and how much I make pop music, which is 0, plus how much she likes ML videos, which is a little bit, and how much I make ML videos, which is 1. So that's where we get a tiny pull of 0.01. So the keys and queries matrices do the magic of extracting the right keys and the right queries, and then multiplying those by using the dot product and calculating how much one word pulls another. And as you can see, it's asymmetric. So to summarize, let's say that we have a long embedding vector for Taylor Swift, and some features are key features because they pull, other are query features because they get pulled, and others may be neither. And the key features are used to pull other words. For example, this guy over here plays football and plays for the Eagle. She likes the NFL and likes the Eagle, so there's a strong pull in that direction. Let's say she's also a Beatles fan. Well, Paul McCartney is a Beatle, so therefore there's a strong pull from her to Paul McCartney. And in the other direction, let's say, for example, Simone Biles. Did you know she's a huge Swiftie? She's also a huge fan of pop music. So she pulls Taylor Swift into her conversations because of that entry that says pop music matching with this fan of pop music. And if we're talking about Grammys, for example, then the Grammy will pull Taylor Swift because there's an entry called is a Grammy, and that matches with the entry called Grammy winner if we have a good key query matrices that pick that up. And so if we're talking about Grammys, then Taylor Swift gets pulled into the conversation. So in general, we have a key and query matrices, and we've seen that they have a great job. The key matrix over here and the query matrix over here help us in different ways. For example, what features are important when comparing words? It's able to stretch and compress dimensions to help us, just like it did with the rabbit, the elephant, and the truck. It also helps us combine features. What features need to be combined when comparing words? And that was the example with the physics and math students. And also it tells us what features will pull other words and what features make the word get pulled, like the fisherman and the net. So that is the key and the query matrices, but there's still more to this. So now you've seen what we can do with one key and one query matrices, but these models are very big and they actually use a lot of key and query matrices. So that's where multi-head attention comes in. So remember that we left an open conversation before because we had the embedding of the math and the physics student, and I said I like it more like this because in my head, the students who like math also like physics and vice versa. So that's my opinion. But maybe you come in and you say, well, I don't think so. I think students who like math and physics can be very different because maybe physics is more experimental and math is more theoretical. So there could be huge differences. And maybe someone else comes in and says, well, actually, I like the first embedding. I like the fact that they're kind of similar, kind of different. So we would just kind of agree to disagree, right? Or we could just say, hey, 3 heads think more than one. And that's multi-head attention. Multi-head attention says several heads think more than one. So each one of these embeddings is going to be one head of attention. We have head 1, head 2, and head 3. And how do we combine them? Well, there's going to be a big mastermind here, a big brain called linear. And what linear is going to do is it's going to give more votes to some of them and less votes to some of them. So it's going to pick a bunch of numbers and add them to each one of these edges and then make them vote or combine them in some way. They would add the results or anything like that, but it would be a weighted sum. So some embeddings will talk louder than others. And the linear step is so smart, it's part of the neural network, that it's going to pick up from the context which heads should be listened to more than others. So for example, let's say if we are in a university career fair, then you put more emphasis to the embedding that says that the math and physics students are similar because maybe you want to send the math and physics students to the same panel or the same conference or something like that. But if you're talking about a scientific conversation, then maybe you really want to tell apart physics and math. They are not so similar anymore because the research goes in different directions. So you would add more emphasis to the third embedding. And you could have a completely different context where you add different weights to the embeddings. But the idea is that this linear step over here is very smart. It's part of the neural network and it will know what weights to add to each embedding. Now, this is an interesting concept, the fact that I'm going to train some different embeddings in different ways, and they're going to pick up some strengths and some weaknesses. When I'm talking about sports, you want this embedding. When I'm talking about cooking, you want this embedding, and so on. Why does that happen? Why is it that they all don't just get trained to do the same thing well? Well, that happens a lot in machine learning, and it also happens with humans. Let's say you have a bunch of people and you want to make them play soccer really well. And if I want to really optimize how they play soccer, the best thing to do is to give them different positions. Somebody's going to be the goalie, somebody's going to defend, midfielder, attacker. It's not going to help so much if they all play in the same position. The team that plays with different positions is the one that's going to win. And that happens in humans, and that also happens in machine learning. Now, I know what you're thinking. What about Total Football by the great Johan Cruyff? Well, even in Total Football, they play different positions. They just switch these positions a lot. But basically, if you take a bunch of humans and you make them do a task together as a team, it's very likely that some of them will end up focusing on their strengths, and those weaknesses of them are going to be covered by the strengths of others. And that also happens in machine learning. So in attention mechanism, that happens. You're going to see that some embeddings pick up some strengths and some embeddings pick up other strengths. Another place where this happens is in mixture of experts, where you have copies of the same model and you make them do something as a team, and you're going to notice that some models become really good at some things and other models become really good at other things. And the simplest example of this is a neural network. In a neural network, every node is trained in the same way, but some nodes pick up some parts of the data and some nodes pick up other parts of the data. So basically, that's how multi-head attention works. But so far, I've told you about keys and queries matrices. I haven't yet told you about the value matrix. So the value matrix is the last one that we're going to see. This one is a little more subtle. So let's look at our original embedding, the one we started with the animalness and the size. And we know that the key and the query matrix are going to give us the pulls, and these pulls are going to be asymmetric. So let's say that elephant pulls rabbit in a different way that rabbit pulls elephant, and the same with truck. Doesn't matter. We figured that out. Now, here's the thing. The original embedding may not be the one we want to use in a transformer. We may want to use a different embedding that is better for talking. This embedding is going to be better for generating the next word, because remember, the transformer, its job is to generate the next word. This original embedding is the best one to find if two words are similar. But this embedding is the best one when it comes to finding the next word in a sentence. And to find this embedding, we multiply by the value matrix. And it's in this embedding over here that we're going to make the moves, those gravitational moves we talked about. Now, this may not be super clear, and as a matter of fact, I'm going to be honest with you, it took me a while to actually believe that we needed a different embedding as opposed to the original one. If that embedding is good to begin with, why do I want to talk in this embedding? Well, let's look at a numerical example. So let's go back to Taylor Swift. This is Taylor Swift's embedding vector over here. And as you saw, some entries are key entries. They're good for pulling other words. Some entries are query entries. They're good for getting pulled. Some may be neither, and as a matter of fact, there could be combinations of entries that become a key or become a query. So it's not just extracting entries, it's actually adding some of them, but that doesn't matter. The fact is, some entries are better for coming up with the next word, and some entries may not be so useful when it comes to coming up with the next word. And the entries that are good, or the combinations of entries that are good for finding the next word in a sentence, are called the values. These are the entries that are relevant in a conversation. So let's say, for example, that being related to pop music shows up a lot in conversation. So we want to have that entry as one of our values. We're going to keep pop music because that one's important. Let's say that Grammy winner is also an important feature in a conversation, because we're talking about Taylor Swift, Grammys are going to show up. So that's another one. And let's say that musician and artist are important together. So we actually want to find the average of these two. So the average of 1 and 0.7 is 0.85. And let's say that these three features, pop music, Grammy winner, and a combination of musician artists, are the best features that we're going to use when we're having a conversation about Taylor Swift. So that's the value vector. So now the way to extract this value vector is by multiplying by a value matrix. This is the value matrix over here. So we're going to do a little bit of matrix multiplication. Notice that this over here is the vector that describes the word. It has 8 entries that completely describe the word. This one over here has 3 entries that are relevant to the conversation. These are the entries that we want when it comes to talking about Taylor Swift. And the matrix is 3 by 8, because here's the 3 and there is the 8. That's no coincidence. So the first column of the matrix is the column corresponding to pop music because it has a 1 in the 5th entry and it takes the 5th entry here and sends it all the way here. The second column corresponds to Grammy winner because it has a 1 in the 6th entry, meaning it takes the 6th entry on the embedding vector and brings it to the value vector. And finally, the last column is the one for musician plus artist divided by 2 because it has a 1/2 in the 4th and 7th entries, meaning it takes these 2 entries over here and averages them out to get this entry here. So basically, the value matrix is the one that takes the embedding vector, the one that describes the word really well, and turns it into the value vector. The value vector is the vector that is optimal when it comes to talking in a conversation. So in summary, we have 3 matrices. The key matrix picks features that pull other words. The query matrix picks features that help the word get pulled by other words. And then the value matrix that picks features that are useful for talking. And with these 3 is that you get a model to talk so well. Now let me summarize this into the attention mechanism. This is the diagram for the attention mechanism. You have your 3 matrices, the keys that pull, the queries that are pulled, and the values that do the talking. This part over here is the one that calculates the similarity, where you have the math multiplication, that's the dot product. Then you have masked attention. I never talked about masked attention, but masked attention says a word doesn't get pulled by all the other words in the sentence. It only gets pulled by the words that come previously. It doesn't see the words that come after. That's what masked attention says. And then this other part is the one that does the talking. So the words get moved in this optimized embedding found by the value matrix. And when you want to do multi-head attention, you do the same thing many times. So you have a lot of different heads of attention. And then you have this linear node on top that is the mastermind that decides how much weight to give to each one of the heads based on the context that's happening, and it combines them into this sort of optimal embedding to do the talking. And as you see, attention shows up in the diagram of a transformer over here in several places. So that's all, folks. Thank you so much for your attention. And if you'd like to follow me, I would really appreciate that. That will actually help me make more videos. Follow my YouTube channel, Serrano Academy. You can actually get more engaged by joining the channel or by supporting me on Patreon. My videos will always be free, but if you support me, you will be helping me make more videos and you'll get some fun perks. For example, you can get early access to videos. You can get some Q&As with me. We've been making some Q&As that are a lot of fun with a few of the members. So they actually get to ask me any question they want. And you can also get your name on the videos. You can also follow me on Twitter, Serrano Academy, or check out my page, serrano.academy, where I have blog posts, I have code, courses, anything you want. I also have a book called Grokking Machine Learning, which I explain supervised learning using fun analogies and fun examples, and also a lot of code. Here is a discount code, Serrano YT. You can get a 40% discount code. The link is in the comments of the video. So thank you very much and see you in the next video.